Hi everyone, and welcome to week 7 of Introduction to Complex Systems. This week we will continue looking at dynamical systems. First, let's review what we did in our last lecture. Last time we started looking at dynamical systems. So we looked at discrete dynamical systems, which are described by iterative maps. We considered some examples, and then we moved to continuous dynamical systems described by differential equations. We looked at some of the tools for visualizing the dynamics, time series plots and phase plot diagrams, and then we focused on finding equilibrium points and determining the asymptotic behaviors and the stability using the Jacobian matrix. Last week was based on the chapters 3 and 7 of Hiroki Sayama, and today we continue with dynamical systems, focusing on the next two chapters of Hiroki Sayama, so chapters 8 and 9. This week we'll start it with bifurcation analysis, and so bifurcation analysis is all about looking at how the stability of equilibrium points can change as you vary some parameter in your dynamical systems. So it is connected to things like catastrophe theory and phase transitions. When you have a small change in your in some of the parameters can lead to drastic outcomes in the dynamics of the systems. So we want to look at some of the analytic techniques for detecting these critical transitions. And then we will have a brief introduction into chaos theory. So we will look at some basic techniques for detecting chaotic dynamics. So bifurcation diagrams and Lyapunov exponents. And finally, we'll have an introduction to Taken's embedding. Okay, let's start with bifurcations. So bifurcation is a qualitative topological change of a system's phase space that occurs when some parameters are slightly varied across the critical thresholds. Well, last week we looked at the conditions for stability, and if you recall that stability, to determine the stability, we had to look at for continuous time models, we had to look at the real parts of dominant eigenvalues. So if they were negative, the system was stable, and if they were positive, the system is unstable. Thus, the critical point where the bifurcation occurs is when the real part of the dominant eigenvalue is 0, equals to 0. We did not really look into much. We didn't really look into at least we didn't have any example for determining stability in discrete time models. They were slightly different, so there you have to look at the absolute values of the eigenvalues, and they had to be less or equal, or less or greater than 1, depending on whether your system is stable or unstable. But so I mean, this is described in more depth in the Hiroki Sayama book, but naturally the condition here is equality for bifurcation in discrete time models. So I think this will become clear when we will look into the examples, and particularly when we walk through an example using a Mathematica notebook. But first, let's look at the calculation let's look at the calculation from chapter 8 in Hiroki Sayama, where they take a very simple continuous dynamical system with one parameter. So the function f here is r minus x squared. It's very simple. And then they do a bifurcation analysis on this. So at what values of r we have a qualitative change in our structure of equilibrium points. So let's have a look briefly at this calculation. So the first step of the bifurcation analysis is to determine the location of equilibrium points, and the equilibrium point is when the derivative is 0, or in other words, when the f of x equals to 0. So this gives us a quadratic equation, and the solution is simply plus minus square root of r. So now let's do the bifurcation analysis part. So there we have to determine the stability, recall, we have to look at the Jacobian matrix. So let's do that. In this case, the Jacobian matrix is simply a scalar, because essentially it's a 1-by-1 matrix, because we only have 1 degree of freedom x. So the Jacobian is simply a derivative of f with respect to x evaluated at the equilibrium point. So let's evaluate this. So derivative of f with respect to x is well, it's 2x. It actually should be it should be, the condition is it actually should be minus 2x. I made a mistake here. It's minus 2x, but when you plug in the value for the value x equilibrium, it's just plus minus square root of r, so you end up with plus minus 2 of square root of r. Thus this can only be satisfied, so this equation, when r is equals to 0, r equals to 0. So this is where the bifurcation occurs, right? When r is less than 0, then we have a square root of negative number, which is not allowed. And when r is greater than 0, then it's okay. You have two equilibrium points which are plus or minus square root of r. So we cannot have imaginary numbers here, because we restrict x. X is a real number. So let's summarize these findings on the table. Okay, so equilibrium points, you have two, so square root of r and minus square root of r. So for r less than 0, we do not have the equilibrium point, because square root of minus r is an imaginary number, which is not allowed here. But for r is greater than 0, we have two equilibrium points. One stable, one unstable. So if we can actually do a following plot. On the x-axis, represents r, and on the y-axis we have x equilibrium. So now the square root of r is going to be the blue line, and minus square root of r is going to be the red dashed line. And this kind of plot is a bifurcation diagram. What does it mean? Well, it means that if r is negative, we do not have any equilibrium points. When r is positive, we have two equilibrium points, one stable, one unstable. When r is 0, we have a critical point. This is where the qualitative change happens. So on the one hand, we no equilibrium points, on the other hand, two equilibrium points. So this is a qualitative change, and this is a bifurcation point. Visually, you can think of if you move from this side to from right to left, it looks like the two points collide and annihilate. And if you move from here to here, it's as if they are created. Right. This is called a saddle node bifurcation. You can also draw arrows which represent how would the system move if you. So if you are at x equals to 4, for example, and r equals to 2.5, then you would move such that you are attracted to this equilibrium point. So this is just a pictorial representation emphasizing the stability of the equilibrium point. So if the arrows point towards the line, this is a stable equilibrium point, and if they point away, this is an unstable equilibrium point. But you don't have to draw this really. Now, there are many types of bifurcations. So as I said, this type of bifurcation is called saddle point bifurcation. You can have a bifurcation which looks like this, where you have two equilibrium points, stable and unstable. They move towards each other, and then they collide here, and then they exchange stabilities. This type of bifurcation is called transcritical bifurcation. You can also have pitchfork bifurcation, where you have a stable equilibrium point split it into two stable and one unstable, or the other way around, where you have an unstable equilibrium point split into two unstable and unstable. So this actually often in physics it is called a second order phase transition, where you have for instance, a paramagnet is on this side, and then a ferromagnet is on this side. So if ferromagnet can be magnetized either up or down, and so this is often you're talking about pitchfork bifurcation when in the context of second order phase transitions. But there are of course many other examples of pitchfork bifurcations. And then you can actually imagine putting several bifurcations into you can have a system which has several bifurcations, right? So For instance, in this case, you have two saddle node bifurcations, so one here and one here. And I think it will be this particular example will be good to go through in more detail. So this bifurcation you can get from this equation. So let's do a detailed analysis of this differential equation. And I prepared a mathematical notebook just for that.